Hi, everybody. Dr. White here. We're beginning a new chapter, and we're going to talk about now functions of one random variable where it could be either a discrete or a continuous random variable. We've kind of touched on these on this topic before through the course of the semester and done little bits of things. Like, we can find the expected value for a function of a random variable and things like that. But now we're going for the whole hog. We want to be able to figure out everything about a given function of a given random variable, like be able to find its CDF or its PDF if we want. So let's begin with a simple example involving a discrete random variable, just to show you that everything we do is ultimately going to be founded in some common sense stuff that you could think up on your own in some cases. So let's let capital X be some random variable which has these possible values here. So that's its sample space. It's those 8 possible numbers. And let's say it's equally likely to take on each of those numbers. So the PMF is f of x equals 1/8 for each of those numbers. Let's take a transformation of that random variable. How about the square of it? And what's the PDF for that new random variable, capital Y? So I'm just kind of following some conventions that the book silently introduces here. Your original random variable has a PDF of little f. Your new one has a PDF of little g. So that's the probability that capital Y is little y. Okay. And so you can kind of back solve it, basically. You just say, well, that's the probability that x squared is y. And so all we got to do is really find all the values of little x where little x squared would make y and add up their PMFs. That's all we got to do. Total common sense. So in this case, I'll make a little table down here of the x values and their squares. And I see that actually there's a couple of ways to get a 4, and there's a couple of ways to get a 1. You could get a 4 by squaring -2, and you could get a 4 by squaring 2. And similarly, there's a couple of ways to get your 1 for your y random variable. And so we're going to have to add 1/8 and 1/8 together for those ways. So the result of this summation is going to be a 2/8 if little y is 1 or 4, but it'll be just a 1/8 for the other possible values of little y, the other squares. Okay, simple enough. Let's take another discrete random variable. How about let's let capital X have the Poisson distribution with rate lambda of 4. Okay, so heading back to our heads where we have just memorized the PDF for Poissons, we know that the PMF is 4 to the x e to the minus 4 over x factorial for the non-negative integers. Okay, let's grab a transformation. How about y is the square root of x? And so the possible y's are square root of 0, square root of 1, square root of 2, square root of 3, and so on. And one kind of convenient thing about this situation compared to the previous example is that our transformation is a one-to-one function. If you graph y equals square root of x, it's always increasing. And so, if you draw a horizontal line through the graph, it'll only hit the graph once. So there's only ever one x that goes to a given y. One-to-one function. And whenever that happens, that's convenient because you don't have to think about adding up different little pieces of stuff. It's going to work out much easier for you when you do the back solving. So our probability mass function for y, the little g of y, is going to turn into, back solving approach, the probability that square root of x is y. And so we got to sum up over all of the x's whose square root is little y, and that'll be just one of them each time, f of x. So You could also think of the x's as being the x's that are the squares of y's, the squares of these square root variables as well. That's totally fine as well. And when you think about it that way, it's kind of a little bit easier to proceed in the sum, because now you can just think of the x as y squared, and there you go. And there's only one of them because of the one-to-oneness. You're not adding anything together ever. And so you just have to stick in a y square wherever you saw an x over here in the formula for the PDF of capital X. And so you get this stuff. It's just that the support is this different thing. Okay. So there we are dealing with things when x is discrete random variable. What if x is a continuous random variable? So there's a couple of popular ways to go. One is called the CDF technique. It's actually something that we've worked with before. And then another is called the change of variables technique, which we'll go ahead and introduce this time in this section. So the idea of the CDF technique is that if y is some function of x, like it's u of x, where u is some function, and you want the marginal, and you want the CDF for y, let's call that CDF capital G. How about it? So if you want probability that capital Y is less than or equal to little y, then it's going to be the same kind of back-solving idea. You're going to look for the probability that u of x is less than or equal to y, and you're going to hope you can, like, that's an event there. You'd like to express that event in terms of x being less than or bigger than a number instead of the u of x. So it's like back-solving the event for x, which you'll typically be able to do most easily if the u is a one-to-one function. But once you kind of like got it as probability that capital X is less than or equal to something, well, you know the CDF for X, and so you'll be able to continue and find the CDF for Y. And then once you got the CDF for Y, you can learn anything else you want about Y. Take the derivative to get a PDF, integrate to get probabilities, whatever you want. So let's pull out an example of this kind of technique. It's a fun one too. Let's look at a situation right here. So I've got the x-axis here on the bottom. I've got the y-axis vertically. And so this is the origin, basically. And I've got this point 0, 1 where I'm waving my little cursor right now, okay? And I've got this arrow, okay? And I'm thinking about that arrow as like a spinner. It's like somebody could flick it. And it would just spin, 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 and it would be like equally likely to land at any angle. So, of course, there's a 50% chance that the spinner is just going to land pointing like up, in which case I just throw that away. So I'm only going to look at what happens if the spinner lands with the arrow pointing down somehow. And when I do that, I'm going to measure the angle between this vertical line here and the spinner, okay? And I'm going to call that angle capital X, okay? And so that's why I'm not calling the horizontal axis the x-axis, really. And also don't want to call the vertical axis the y-axis, because I'm going to use y as a transformation of my capital X variable. Okay, well, what about the distribution of capital X, the distribution of that angle? Well, your spinner, it could land going straight down, in which case that's an angle of 0 radians between the straight down line and the spinner. It could land like practically going all the way over out this way, okay? from the 0, 1, just straight out to the right. That would be an angle of pi over 2 radians. And I guess then if it landed like straight going out to the left, that would be an angle of negative pi over 2 radians. Now, of course, the chance that it would land on pi over 2 or negative pi over 2, either one of those has chance 0, this being a continuous type random variable. So I'm just going to consider the angles in between. And it's equally likely to be any angle between minus pi over 2 and pi over 2. So actually, x has a uniform distribution from minus pi over 2 to pi over 2. Okay. Now, in the situation that I've drawn here, I've got a right triangle with an angle of x up here. And, you know, this side here going down from the 0, 1 to the origin, that's of length 1. And we know that tangent of an angle is opposite divided by adjacent. So that means that this opposite side here, the one going out from the origin to the point where the spinner crosses the x-axis, that length has to be tangent of x in order for the ratio opposite over adjacent to make tangent of x. And I'm interested in that tangent of x length. And it's a random variable because the x is a random variable. So I set it up like that. Y is tangent of capital X. Y is a transformation of the capital X random variable, and I want to investigate its distribution. So one thing you should notice right away is that its support is the entire real line. You know, because that spinner, it could, as it covers its possible angles, it can point way, way back to the negative, the negative numbers on the horizontal axis, or way, way forward and hit big positive numbers on the horizontal axis. It could hit any real number at all. Okay. How about the CDF for X? I'm going to need that in order to be able to figure out the CDF for Y. So let's set that up. So I think about how CDFs work for uniform random variables. Their value is 0 before the lowest possible value of the random variable. Their value is 1 after the upper bound on the uniform. But in between the bounds, it's the x value minus the lower bound divided by the upper bound minus the lower bound. So if I simplify that a little bit, I get that this is the CDF for capital X. Okay, sorry about that. So let's head to the CDF technique and see if we can grab the CDF for capital Y. So CDF for the capital Y is capital G of Y. Probability that y is less than or equal to y. Probability that tangent of x is less than or equal to y. Back solve for x. So we're looking at the probability that x is less than or equal to the arctangent of y. Okay. And by the way, the tangent function, if you look at its graph, you know, like in a Calc 2, Calculus 1 textbook or graphing and graphing calculator, you'll see that for x's between minus pi over 2 and pi over 2, it's a 1-to-1 graph. So you can totally back solve. You get a unique answer for your arctangent. Okay, but we know the chance that x is less than a number. According to this, it's got to be, you just plug in that for x. I know that I go here and not in these other places. As long as the y is between minus infinity to infinity, it means I landed somewhere. And that meant the angle had to be between minus pi over 2 and pi over 2. So I've got to go here and plug in there. And so I plug in my arctangent of y right there. And so that's the probability that capital Y is less than or equal to little y. Which is not too illuminating, So why don't we take the derivative of the CDF and get ourselves a PDF for capital Y. So we do that. And the derivative of arctangent of something is 1 over 1 plus the something squared. So 1 over 1 plus y squared. Now, there's also a plus pi over 2 on the top, but its derivative is 0. Now, I am multiplying the whole thing, the top, by 1 over pi, so that constant multiple stays around, and this would therefore be the derivative. That's good for all your y's. So if I were to draw a rough graph of the PDF, here I have like a y-axis and then like a height axis. When y is 0, this works out to, oops, and that's a typo. That should be a 1 over pi there, not a pi. I will consider running off a scan with the correction there, but that's not a pi. It's a 1 over pi. And then the graph gets lower for any non-zero values of y. And the bigger y is, positive or negative, the lower the graph is going to be. So anyway, this random variable is called the Cauchy distribution. Cauchy was a famous 19th century mathematician. And it's a pretty interesting distribution. For one thing, its expected value does not exist. You'll prove this in a homework. And it kind of makes sense that maybe it doesn't, because you look at this as 1 over y squared. And if you had to integrate to get an expected value, you'd be integrating like a y times a 1 over y squared. So you'd be doing the integral of like a 1 over y, out to infinity. And, well, when you do improper integrals with 1 over y, you already know from your Calc 2 stuff, that kind of stuff diverges. That 1 over y goes to 0 too slow to have a finite area underneath it all the way out to infinity. So basically what's happening here, and you'll prove it exactly when you do the math with the improper integrals, is the tails are too big. Even though this curve is perfectly symmetric around 0, the tails are just too big for the random variable to settle down to anything on average if you try it a lot of times and average up your results. It just won't settle down. It's really neat. Okay, so let's turn from the CDF method now to what we call the change of variables technique. It's based on a theorem that's really the substitution method back from Calc 1. But it's specialized here to the situation where we're dealing with PDFs as our functions. So let's let x be a random variable with PDF f of x. And let's let y be some transformation u of x, where that function u is monotone increasing or monotone decreasing, okay? Either one. And also it needs to be differentiable. Well, since it's like either increasing or decreasing, it's got to be 1-to-1. So it's going to have an inverse function. And in calculus theory, you learned that the inverse function, would also be differentiable and all that kind of stuff. So let's call that inverse function nu. Not really v. I'm following the textbook, and my eyes are a little bad, but I think they're writing a nu there. So, so let's just call it nu. Well, here's the theorem. Here's what you get. The PDF for your transform, little g of y, is f, where you just plug in the v of y expression for the x. And you multiply by the absolute value of the derivative of that inverse function at y. And this is good for all y's in support of big Y. Otherwise, of course, it's 0. So in the book, they give the proof, and it'll be just like whatever proof you saw in your calculus book, that the substitution method really does work to find definite integrals. So let's give that method a try. So I'm just going to try like exercise 3 here out of the book. So say X has this PDF, 4x cubed, with support X's between 0 and 1. So I won't stop to show that that's really a PDF, but you could verify yourself that the definite integral from 0 to 1 of 4x cubed does turn out to be 1. And let's let y be the following transformation of capital X. Let it be capital X squared. So the support of y would also be everything from 0 to 1. When you square something between 0 and 1, you still come out with something between 0 and 1. It's always good to first think about what would be the support of your transformation. Also, although the function x squared is not one-to-one on all real numbers, it is one-to-one when you restrict the domain to be just the x's from 0 to 1. And the other thing I notice is that it's monotone increasing on that interval. So we can totally apply this change of variables technique. So what I need to do is I first need to find the inverse function for my u. So I think, okay, u of x is x squared. I'm going to call u of x y. And then I'll just solve for the x. And so I take the square root of both sides, and I get x is the square root of y. So the inverse function at y is the square root of y. And so I'll just call that inverse function nu, because the book likes to do that. So nu of y is square root of y. And I'm going to need nu prime of y, so I go ahead and get it 1/2 y to the negative half. And then I run to the change of variables technique expression. So I got to plug in my nu of y instead of an x. So I'm going to be plugging in a y to the 1/2. And I got to take the absolute value of nu prime of y. So here's nu prime of y, and I'm here are my absolute value signs still. And so let me see. F of x was 4x cubed, so we are looking at a 4 y to the halves cubed. And y is between 0 and 1, so the square root of it is this totally well-defined real number, which is also positive. So I can just go ahead and take off those absolute value signs. And a little simplification leads me to 2y. And that's good for all the y's over the entire support. So if I were to make a graph of the PDF for y, it looks like that. It rises in a straight line from the origin up to the point 1, 2. Otherwise, it's just 0. So an unexciting example, but it gives us the idea for how to apply this technique. Let me try another example where I'm basically going to be using the CDF technique on it instead of a change of variables. So let's let capital F of x be the CDF for some continuous distribution. That not just any one in the world, but one that is 0 up until some number a, and then it rises without ever, it rises in a one-to-one way. So it doesn't stay flat for any interval at all. It might like slow down its rise. It might even like flatten for an instant and then continue to rise, but it's got to rise in a one-to-one way. And then it hits a number b where it gets to be 1, and of course it's going to stay at 1. Okay. So such a function would definitely be invertible. On the, and that's a typo, it's not 0 to 1, it's well, actually, it's invertible. It's invertible, or sorry, it's 1-to-1 between a and b, and so its inverse exists. If you just restrict to your domain to be between a and b, then your f values would be between 0 and 1, and you have a 1-to-1 function there the inverse would have a domain from 0 to 1, and it would take things back to numbers between A and B. So the inverse totally exists, just saying that. Okay. Now, just take a uniform 0, 1 random variable, equally likely to be any number between 0 and 1. And take that inverse function that we've just looked at and apply it to that uniform. So that is a totally decent transformation of the uniform. Now we're kind of switching around our letters from the way the book usually does it. This x is now the transform of some original random variable, a y. But conceptually, we're investigating the same thing. We would like to know the distribution of that transform of capital Y. So why don't we get it CDF? So we want the chance that it's less than or equal to little x, which is the chance that f inverse of capital Y is less than or equal to little x. Back solving, that's the chance that capital Y is less than or equal to f of x. That can be done. The back solving can be done because of the one-to-oneness. But hey, think about the CDF for capital Y. For little y's between 0 and 1, it's the y minus 0 over the 1 minus 0. It's just y. And this capital F is somewhere between 0 and 1. And so the value is capital F. So the chance that our x random variable is less than or equal to x is the same as the chances of whatever random variable had that CDF to be less than or equal to x. And so you might be like, what possible use is this? Well, say that you've got a probability distribution that you would like to do simulation with. You would like to get random values from it. You know? So like, you know, if it were a uniform or a normal or, you know, a chi-square or a gamma or an exponential, R already has these like built-in ways to give you random values. But like, what if all you knew was the math stuff about the distribution, like you knew it's CDF, okay? Like you knew it was this. There's some like formula for this. Then all you got to do is take the inverse of that function, apply it to a random uniform, and you get something that's random of the distribution you wanted to simulate. And so basically, like in R, and we'll try this out, you'd just be doing F inverse of R unif, asking for one random value, then it's 0 and x is 1. And that would give you one random value for that distribution whose CDF is capital F. So we should definitely try this out. We will. This corresponds to theorem 5.1-1 in the textbook. Now, the change of variables technique really depended on the function u being 1 to 1. So you're not going to be able to use change of variables when u is not 1 to 1. You're really going to have to use the CDF technique, and you'll have to be a little careful in your thinking too, because there'll not be like more than one way to get a value. Here's a simple example of a situation like that. So this is exercise 17, part B in the book. Say that x has this PDF, 3/2 x squared, x is between -1 and 1. So here's a graph of the PDF, and well, not quite, because it's just y equals x squared, not 3/2 x squared. Oh, I'm sorry. Whoa, I'm getting ahead of myself. This is not the graph of f. Say that y is x squared, and say that we want to know the distribution of y. So I think about that function, u of x equals x squared. So here's its graph. And that is not one-to-one on this support here for capital X. So let's keep that in mind when we try the CDF technique. CDF for capital Y, probability of capital Y is less than or equal to little y, is probability that x squared is less than or equal to y. And that is not the probability that x is less than or equal to square root of y. No, no, no. X has to be less than or equal to square root of y and bigger than negative the square root of y. Because if x were like all the way down, as far as it could go, down to -1, its square would be 1, which might very well be bigger than the y we're talking about. So it's only in this little sub-interval of -1 to 1 that we're looking at. And so we're having to integrate from -root y to root y, 3/2 x squared dx. And so you can see where the non-one-to-oneness is coming in. It's like there's going to be two values of x that correspond to the same x squared, a negative value and a plus value. And we're capturing both of them when we do this. So we apply the fundamental theorem of calculus, and it ain't so bad. And so that would be the CDF. Y to the 3/2, 0 less than y, less than 1. And if you needed the PDF, great. It's just the derivative on that same support. Y'all see why it's 0 to 1? Because when you square the x's, you're squaring stuff from -1 to 1. You'll have to come out between 0 and 1. I should have said 0 less than or equal to y less than 1. 0 is totally in the support, but the value is 0. I'm going to go ahead and change that so that. Got it. So I do want to try out that theorem 5.11. So why don't we try to figure out how to simulate that random variable x up here, the one that has this PDF. Okay. So I'll go ahead and get its CDF. And so I integrate -infinity to x. Oops, that's wrong. That should say -infinity to x, little f of t dt. I'll change that. But the support is only from -1 to 1. And so I only have to go -1 up to my x. And on that support, it's 3/2 t squared. Okay. I just use t variable here because I got to use a different dummy variable than my upper limit x. So I apply the fundamental theorem of calculus, and I crank a little bit, and I get this. And that's good for all of the x's in the support. So as a piecewise defined function, f of x would look like this. So it's like 0 until we get to -1. And then it rises like a cubic. And it actually like flattens out for an instant, right when x is 0, the derivative is 0 there. And it rises again. But because it only flattens out for an instant, it actually stays 1 to 1. Until it hits x is 1, of course, at which point it stays 1. So it fits the conditions that we need to apply this theorem 5.1 number 1. There's an a value where it's 0 and a b value where it's 1, and it's like in between. So let's go ahead and get its inverse. So I'm going to set y to be x cubed plus 1 over 2. And I'm going to get its inverse inside that little interval from -1 to 1. So I solve for the x, and I get x is 2 minus 1 to the 1/3 power. And that's on the y's between 0 and 1, because that's the y values that you get for this capital F function as you go over the domain from -1 to 1. Now, I like to write functions as functions of x, particularly if I'm going to apply this theorem up here, where I'm thinking about, f of x. So I'll write that function as, let me get that down. So I'll write it as f inverse of x is 2x minus 1 to the 1/3. And now I've grabbed myself a uniform 0, 1 function, and I say I need to look at the following transformation of uniform f inverse of u. The theorem says that's going to have the same distribution as my random variable x that I started with up here. So I'm going to head to R with that. I'm going to do f inverse. I'm going to do like twice uniform minus 1 to the 1/3 power. And I'll be able to simulate this new random variable. That's going to be really cool. And so I'll do that in a separate screencast. So I'll see you soon.